Today we will see whether rotation is a vector or a scalar, and first we'll see it experimentally, then also mathematically. And whether a rotation is a vector or a scalar depends on the magnitude of rotation. A very small rotation, infinitesimally small rotations behave differently, and a finite rotation behave differently. So first explore whether a finite rotation is a scalar or a vector. If finite rotation is a vector, and we know that a vector follows a commutative law, so the rotation will also follow the commutative law. So starting from the same initial orientation, if we give two rotations in different order, and the body finally arrives to the same orientation, then we'll say that these rotations are the vector. And if it doesn't, so we'll say that it is not a vector. So let's see whether a finite rotation is a vector or a scalar. So this is a body I already written because it is a one color, so that we can identify from where we started. So I have written on each face a different letter. So what I will do, I will start the body from this orientation. You will be seeing A written over here, and from this position, this is going to be my x-axis and this is going to be my y-axis. So I will give it two rotations of 90 degree each. First along x-axis in this direction, in the anti-clockwise direction, as you can see, and here then along y direction. Observer here will also see that along the anti-clockwise direction. So these two rotation I will give first and see on what orientation the body arrives. Then again, starting from the same position, I will reverse the order. First rotation along the y-axis and then rotation along the x-axis. If the body arrives to the same position finally, so we can say that this finite rotation is a vector, and if it doesn't arrive, so we can say it is a not vector, again it is a scalar. So here we go. So this is a body and this is my x-axis, so I will give it a 90 degree rotation about this axis, and if I give a 90 degree rotation, it arrives to this position. So that is the first rotation. And now what I will do, I will give it a 90 degree rotation about the y-axis in the counterclockwise direction, and it will reach to this position. So you can see here what is written. This is E in the horizontal position, right? So this is the position we got. Now start again. Now start again from the same initial position, and what we'll do, we will first rotate it counterclockwise in the along the about y-axis. So I give a 90 degree rotation and the body reaches to this position, and you can see this position, it is written D over here. And now what I will do, I will do this, rotate this about x-axis in the counterclockwise direction, again a 90 degree rotation. So it is arriving to this, and this is D, and D not in the position, right position, but in the previous way we had got the E, and now we are getting D. So this is these two orientation that we are getting are not same. So what we can say, we can say that the finite rotation is not a vector quantity, and I can show it diagrammatically also. So suppose this is a body, a rectangular body, and this is a rectangular body, and suppose this is some can, and this is a can, and A is written here and B is written here, and we have three axes. This is say x-axis, and this is y-axis, and this is the z-axis. So what we are going to do, we have to do two rotations. The first rotation is about x-axis, counterclockwise direction, a 90 degree rotation, and the second rotation is about this axis, So right now what we'll do, this will be my first rotation and this will be my second rotation. So if I rotate it first, so what I will see, I will get, if I perform the first rotation, so what I'm going to get, the orientation of the body would be something like this, and that would be something like this. This face will become horizontal and this face will become vertical and this face will become horizontal. So after completing the first orientation, first rotation, rotation 1, so this uh, body will come to this position and the B that was here, this B will come to here, and the side that was here and this side will come here, so my A will come to this position and the cap that was here, that will be somewhere here, so which will not be visible from this position. Now if we rotate it, about y-axis, so what will happen now if we rotate it about y-axis, so this side, this face will come in the front position, so that was the first rotation. And now after the second rotation, what orientation we are going to get, this orientation, and A will go below this surface, so this is going to be the orientation of the body and the B will become like this. So what we have done, we have given this first rotation of 90 degree about x-axis first and then about y-axis. So this is the final orientation. Now what we can do, now we will rotate it about second first, then first. So if we in the second way, that was the first way, in the second way, if I rotate it about y-axis counterclockwise 90 degree first, so the orientation that we are going to get would be like this. This would be here and that would be here. That whole thing, this will come in front of us, and this is going to be like that, and this the cap that was here, this cap will come here, and the B that was here, that B will come here, so it will be along this position. And now we have to rotate it this way. So if we rotate it this way, so the body will take this orientation and it will appear almost similar, but this B will come here, so this B will come here, so B will come here like this, and this cap will come, the cap that was here, so this cap will come here. So we can see that the final two orientation in reversing the order of rotation are different. So what we can say that finite rotation is not a vector, and infinitesimally small rotation is a vector or not, that we have to explore. Now this was experimentally, and now we'll do it more mathematically, whether finite angular rotation is a vector or a scalar. So let's see this. Now let's see mathematically whether rotation is a scalar or vector. So for this we have this coordinate axis. These are our x-axis, y-axis and z-axis, and I want to take a body of unit length. Suppose I take a body of unit length, this is a body, and I am putting a handle over here, and suppose I have taken a body of unit length 1. So this coordinate is 0, 0, and the coordinate of this point is 0, 0, 1. So I will give this body two rotations. One is a rotation of delta theta x. Delta theta x is one rotation. Rotation of of angle theta about x-axis and in this sense. So that is our delta theta x, and then I will give it rotation of delta theta y, and this is a rotation of the same angle theta, but that would be about y-axis and along this direction. So that would be the rotation delta theta y. So in any case, whatever way we will rotate, this point is not going to move, this point is going to move. So first what we will do, first we will do the rotation in this order. First delta theta x and then delta theta y, and then what we are going to do, the order change, first delta theta y and then delta theta x, delta theta x. So that would be our first rotation, second order, and this would be first, second. So we'll like to see what is the orientation of the body. I told you that this point will not change and this point will change. So what I am going to do, I am going to find the coordinate of this point. Say this is A and B. A will remain at origin. Coordinates of B after these two rotation in case 1 and case 2. So that I am going to find the coordinates of B. So what will the coordinates of B here, and what will be coordinates of B there? So if they are same, so we will say that this finite rotation of finite or whatever rotation is a vector, otherwise it is a not vector. So this we are going to find here, and coordinates of B in this case we will going to find. So let's start. And okay, before that what we can do, suppose this is a rigid body and these are the coordinate axis, x-axis, y-axis and z-axis, and this body is rotating about z-axis. So any point here is moving in a circle about z-axis. Suppose there is some point and this is moving like about this in z-axis, and this coordinate at certain moment is x, y, z. Now as this body is rotating, so this particle will take different coordinates in different time, but what we can see that the axis about which is moving, that is z-axis, so its z coordinate will not change. So after some time, so what you will say that its x coordinate may become x dash, y coordinate may become y dash, but z coordinate will not change. So same thing will happen if a body rotates about x-axis, its x coordinate will not change, and a body rotates about y-axis, so its y coordinate will not change. So now let's start here. So what we are going to do, we are going to give it a rotation about x-axis first. So that is a pure rotation. So this point will move in a circle of radius 1 centered here. So this point will move in this circle like this, and if we give a rotation of theta, so it will arrive to this position, that is after completion of this. Suppose this angle is theta, so now what is the coordinate of this point? So because we have rotated about x-axis, so this x coordinate has not changed, that is a 0. Y coordinate, this length is 1, and if I make a perpendicular here and a perpendicular here, so the length of this perpendicular is 1 sine theta, so that is a sine theta, and this length would be cos theta, so this is a cos theta. So the y coordinate, this length is the y coordinate, so y coordinate is sine theta here, and z coordinate is cos theta, Okay, so now I am removing this. Now we have to rotate this body about y-axis. I will not look to the whole body. Now I am looking to the this point. So this point is rotating about the y-axis. So if this point is rotating about the y-axis, so the path of this point, the path of B would be circle, and the center would be on the y-axis. The center of the circle will be obtained by dropping a perpendicular. So if we look to the motion of B, so that will be a circle whose center would be here. And what would be the radius? The radius would be this much, and this is nothing but the z coordinate. So from here, from this point, if you look, so this point would be appearing to be moving in a circle whose center would be here, and radius would be how much? The radius would be just cos theta. So now, so this point will be moving. This point will be moving in this circle. This circle. So in this plane. In this plane. So earlier it was moving in. Okay, can take the other one. Earlier it was moving in this plane. Now it is moving in this plane. So now, and the radius of this is cos theta. This is moving in a radius of cos theta. So the radius is cos theta. Then it performed another rotation. So after another rotation, the body, this point B has come here. This point B has come here, and it has performed another rotation like this. So this line is parallel to x-axis. So if I show it here, so this is parallel to z-axis like this. This is z-axis, and this is parallel to x-axis. So I can show it here. And the body moved in the circle of radius what? Cos theta. So this radius is cos theta. This is cos theta, and this was the rotation theta. So if this rotation is theta, so this length will be cos square theta, and this length will be sine theta into cos theta. So sine theta cos theta can be written as this sine theta cos theta can be written as simplify sine 2 theta by 2. So now see, what is the x coordinate? This is the x coordinate, which is sine 2 theta by 2. So this point will have a x coordinate. This point will have a x coordinate here. So this length will be the x coordinate, or this length will be the x coordinate. This is the sine theta cos theta. So sine 2 theta by 2. And the y coordinate did not change because it was moving about y-axis. So y coordinate will be just sine theta. And z coordinate, the z coordinate now has become this much, and that has become how much? That has become cos square theta. So this point has arrived here, and because we know that this point remains fixed, so overall rod has arrived to this position. So after these set of two rotations, the coordinates of the B point have become, what coordinates have become? The coordinates have become sine 2 theta, sine theta, and should write it here, cos square theta. So now I am removing this thing, and I will do the same thing, but now with the reverse order. So again, let's start. This is z-axis, this is y-axis, and this is the x-axis. So this is our body. This point is A and this is B. So its coordinate is 0, 0, 1. And now what we are going to do, we are going to rotate about the y-axis first. So it will move like this. So it will move in the circle like this, and suppose it has come to this position. It has come to this position. like this. So this is a position and this rotation is theta. So what will the coordinate? So now this thing would be, this length would be, this length will become, this is a 1. So that length will become cos theta and this length will become sin theta. Because we have rotated about the y axis, so y coordinate will not change. So this coordinate will become, the x coordinate has become the sin theta. X coordinate has become sin theta, y coordinate is 0, and z coordinate has become cos theta, right? And now what we have to do, now we have to rotate it about the x axis like this. So again we'll look the motion of this point. This point will move in a circle, the center will be here, so radius will be, this point will move in a radius of length cos theta, right? This will move in a radius of length cos theta about x axis. So the motion of the plane would be like, so this will be moving like this. So after, from this position, after this position, after a rotation of theta, it reaches here, suppose here. So this reaches here. So now we want to find the coordinate of this point. So because the motion is in this plane, this is the zy plane, so it is in a zy plane. So let me draw z axis here and y axis here, and the radius is cos theta, so it move in this radius. So this is a cos theta, this length is cos theta, it arrived here. So this length is cos theta, this is theta. So how much will this length be? This length will be just cos square theta, and this length would be how much? This length would be sin theta into cos theta, and again sin theta into cos theta will become what? Sin 2 theta by 2. So it is quite complicated, but nevertheless worth doing it. So the coordinates will become, because it was rotating about x axis from this position, so this coordinate, whatever was the x coordinate here, will not change. So x coordinate will remain sin theta, and y coordinate, this is the y coordinate, so y coordinate has become sin 2 theta by 2, and z coordinate has become cos square theta. So the final orientation, this theta is any general angle, so final orientation, the final orientation of the body, because this point would still be here, now this point has come here, so now this orientation has become this. So looking this and this, we cannot differentiate that way, so that's why we have found the coordinates. So the coordinate of this point has become sin theta comma sin 2 theta by 2 comma cos square theta, and this is a general theta. So we can see that these are not different, these are not same, these are different. So what we can conclude, that any finite angular rotation is not vector, because they are not commutating. But what if theta is very small? So what if theta is very small? Let's say that angular rotation in place of theta, that is just d theta. Okay, so if that is just d theta, so what it will become, that will be this will become sin 2 d theta. Actually this was sin 2 theta by 2, this was sin 2 theta by 2, so sin 2 d theta by 2 and sin d theta and cos square d theta, and this will become sin d theta sin 2 d theta by 2 and cos square d theta by 2. We know that if suppose x is tending to 0, very small, then sin x, provided x measures in radian, this tends to x, and cos x tends to 1. So these d theta are very small. So what will happen? This sine 2 theta, this sine 2 theta will become 2 d theta, sine 2 d theta will become 2 d theta, and by 2. So that will be just d theta, and sine d theta will also be d theta, and that will be 1 if the theta is very small. And here again the sine d theta will become d theta, sine 2 theta by 2, sine 2 theta by 2 will become 2 d theta by 2, that will also be d theta. And cos square theta, cos theta tends to 1, so cos square theta also tends to 1, so that will be 1. So now you can see that these orientation, these coordinates are same. So what we can conclude that if rotation is a finite, any general rotation, finite rotation, then that is not a vector, but the rotation is a very small, infinitesimally small, so that can be treated as a vector.